Speaker is Barnali Dash, and she will be talking about surprising behavior of a main sequence pulsar. Yeah, Barnali, you can start.
Yeah, can you hear me now?
Yes, yeah. We can hear you.
We can see your screen also. You can start.
Okay. So hi everyone. So I'm a final year PhD student working with Poonam. So today I'll be talking about what I call main sequence radio pulse emitter and a surprising low frequency behavior of a particular main sequence radio pulse emitter. So I apologize for changing the title. Initially it was main sequence pulsar, but because the acronym become MSP, which people use for millisecond pulsar, I come up with a different name for which the acronym become MRP. Okay, so main sequence radio pulse emitter, as the name suggests, they are main sequence stars, and they are early type stars of spectral type A or B. They have large scale near dipolar surface magnetic field of strength within the range between hundreds of Gauss to several tens of kilogauss. And they emit highly directed coherent radio emission, which are seen as pulses. This is very similar to the radio emission seen from pulsars. The emission mechanism behind the production of such radio emission is the electron cyclotron measure emission. It gives rise to radiation at frequency proportional to the local electron gyro frequency. And this is a very cartoon diagram showing the phenomenon. It is produced near the magnetic polar regions in these ring shaped regions. These are called auroral rings. And the direction of emission is almost perpendicular to the dipole axis. One of the very important properties of this emission is that the resulting emission has very high circular polarization, close to 100%. Now, you are all aware of the lighthouse effect in case of the pulsars, and I'd now like to demonstrate the same effect in case of the MRPs, just to explain how similar the two phenomena are. So this is a very naive diagram. This circle represents the star, and this is the dipole axis. N means north magnetic poles, S means south magnetic poles, and this is the observer. When the star is in this kind of a rotational phase, this pulse will be seen by the observer. So I forgot to mention that although the radiation is originally emitted at right angle to the dipole axis, because of propagation effect, it gets deviated, and that's why I have drawn these bent arrows. So basically, when the star is in this rotational phase, this pulse will be seen by the observer. And this is what is shown here. And in this rotational phase, net line of sight magnetic field, which is shown by this dashed line, is slightly negative. Then, after a gap, this pulse will be seen by the observer, and now the field is slightly positive. Then, after a relatively longer gap, this pulse will be again seen by the observer, and the field is still slightly positive. And finally, this pulse will be seen by the observer, and field has now become negative. So basically, the ECME light curve, it has two pairs of pulses which are seen near the rotational phases where the line of sight magnetic field is zero, and these are called magnetic nulls. And each pair has one pulse coming from the south magnetic poles and other pulse coming from the north magnetic polar regions. And they can be distinguished from each other because they have opposite circular polarizations. The first MRP, which is UVIR, it was discovered in the year 2000 by Trujillo et al. They observed a star at four frequencies 1.4, 5, 15, and 22 gigahertz using the VLM. And at their lowest frequency of observation, they found that there are strong enhancement in flux density at certain rotational phases. Further observation establishes that this is a persistent phenomena, and they have also very high circular polarization. You can also see because this is a Stokes V diagram. And the emission mechanism was eventually found to be ECME, or electron cyclotron measured emission. Currently, 6 more such stars are known, and it might sounds like not a very big number, given that almost 20 years have passed since the discovery of the very first MRP. But the good thing is that all 6 of these MRPs, they have been discovered in the last 1 or 2 years. So the field has really gained momentum in the recent years only. Out of these 6 new stars, 3 are either discovered or confirmed by us using the GMRT at 610 megahertz. So in these 3 panels, I show you the ECME light curve at 610 megahertz in the top panels, and the respective line of sight magnetic field variation with rotational phase. This is for and these different colors represent different circular polarization, which, as I mentioned, corresponds to radiation produced at opposite magnetic poles. And this is for the star HT132880, which was the second discovered main sequence radio pulse emitter. This is for HT35298, and this is for the star HT142990. So MRPs, they were primarily being studied at frequencies above 1 gigahertz, and it revealed that the phenomena in all cases it is absent above 5 gigahertz. But detailed sub-gigahertz study were totally absent until the year 2018. So it basically started with us. We initiated a campaign to search for these stars using the upgraded GMRT, and also to study the already known MRPs at sub-gigahertz frequencies. And as I mentioned, from this survey to search for these objects, we discovered or confirmed 3 MRPs, which I already showed in the previous slides. So today's talk will be about the sub-gigahertz study performed for the first discovered MRP, which is C Virginis. So C Virginis, or in short CUVIR, it's a magnetic chemically peculiar late B star. It has a rotation period of approximately half a day. So these are the typical, not typical. They are the rotation period of these objects are of the order of days, whereas for pulsars these are of the order of seconds or milliseconds. So it is the closest MRP, which is lying at a distance of 80 parsec, and it has a polar magnetic field strength of approximately 4 kilogauss. Because it was the first discovered MRP, and for more than 15 years this was the only known MRPs, it was extensively studied several times, but above 1 gigahertz only. In all those observations, it was found that the star produces only right circularly polarized ECME pulse. That is what is shown here. This is the expectation that the star will have 2 pairs of ECME pulses, one coming from north, other coming from south magnetic poles with opposite circular polarizations. However, CUVIR produces always RCP, or right circular polarized ECME only, which is shown by these red markers. Blue corresponds to left circularly polarized pulse. So it was well accepted that one of the magnetic poles of the star does not produce ECME, and it was attributed to deviation from dipolar topology. Now we, for the first time, observe it over 330 to 800 megahertz using the upgraded GMRT for one full stellar rotation cycle and at 2 epochs, which are in the years 2019 and 2020. And to our surprise, this is what we saw. On the top panels, I show you the light curve at 370 megahertz, and in the bottom panel, I show you the light curve at 687 megahertz. The red and blue markers represent right and left circular polarization respectively. And you can clearly see that there are enhancements in both circular polarization. In fact, LCP is clearly more dominant at lower frequencies. So the stars show a dramatic transition in terms of its behavior as a function of frequency. But this is not the only surprise that we got. Now let us concentrate on this rotational phase range. Here I show you the light curve for obtained from the data taken in the year 2020. Now in this figure I show you the light curve only for this range of rotational phases but for the data taken in the 2019 and 2020, and the y-axis are in log scale. You can clearly see the difference. The maximum flux density here is close to 200 millisensky, whereas here the maximum flux density is around 20 millisensky. To the best of our knowledge, this is the highest flux density that people have ever observed from any MRPs. And clearly it's a rare phenomenon and a transient, and we decided to give it a name, and which is giant pulse, similar to the case of pulsar. And final surprise that we obtain can be seen from this figure. So I mentioned that we observed the star for one full rotation cycle, but that is the full rotational phase coverage was obtained by observing the star on different days. And here I show you the part of the light curves that we obtain for on different days. Top 4 panels are for the data taken in the year 2019, and bottom 2 are for the data taken in 2020.
Barnali, you
Red
have
and
2
blue,
minutes left.
yeah, red and blue again represents right and left circular polarization. And now let us focus our attention to these two rotational phase ranges. You can clearly see that there is this strong enhancement here, but here and here there is nothing. Similarly, there is strong enhancement here, but here and here there is nothing. So it is the first confirmed observation of radio flare from a magnetic early type star. Now it is quite exciting that we saw flare from a magnetic early type star. This is because these stars have very stable magnetic field. I already mentioned that they have large scale near dipolar surface magnetic field. And it is not clear what can create such transient phenomena. Possibilities include presence of a unresolved companion, or it could be an indicator of episodic ejection of magnetically confined plasma. So I will not go into the detail of that, but if anyone is interested, I can talk about it later. Now, clearly our observation shows that low frequency can have, these MRPs, they can show dramatically different behavior as a function of frequencies, and their higher frequency part, above 1 gigahertz, is relatively well explored, but the lower frequency or the sub gigahertz phase space is not. So so to also we found that this main sequence radio pulse emitters, even though they have this stable magnetic field, they can also exhibit transient phenomena. And to understand what is causing them, we really need to observe them in higher number. And because of the very nature of this phenomena, we cannot do targeted observation, and a sky survey is the only way to approach in this case. And that is where SKA will be very much useful. SKA will be an ideal telescope for performing sky surveys, and the very first thing that we can hope is more discovery of MRPs. Also, with the increase in the sample size, it will increase the probability of detecting transient events. In addition, SK low will allow us to go much below 300 megahertz, and hence it offers us an opportunity to explore the dynamic low frequency phase space, which currently we do not have achieved yet. And finally, we will also be able to obtain a low frequency cutoff of ECME, which is currently not known for any of these MRPs. And I'll leave you with the summary. Thank you.
Thank you, Barnali. We can take a few questions. So again, people who are on Zoom, please raise your hand and you can ask the question after that. Yeah, Dipankar, please go ahead.
Hello, Barnali. Nice talk. Now, when you get electrons cyclotron emission,
Yeah.
It is the local resonance frequency, right? The local resonant gyro frequency.
Yeah,
which depends on the magnetic
frequency. Yeah.
So when you go from one frequency to another, from higher frequency to lower frequency, is the emission region going further out from the stellar surface?
Yes, yes.
So is there an idea as to how far this can go? So therefore that will tell you as to what is the lowest frequency up to which you can see this emission?
So I mean, up to the minimum frequency at which ECME can be seen, is that the
Yeah, because in many cases we do see this ECME, for example, in auroral emission, in
Yeah.
planets, or in Jupiter's magnetosphere, in brown dwarfs. Typically, there is a limited bandwidth over which ECME can be seen.
yes,
And
yes,
below
yes.
that and above that, it drops. So, is there some idea as to over
Yeah.
what range of frequencies this can be?
So the theoretically we expect that ECME should not be seen if the ratio between plasma frequency and electron local electron frequency is of the order of 1. But till now, because there are very few low frequency observation, for none of these MRPs we know the lower frequency limit. So we are yet to go that below. So observationally, it's totally unconstrained yet.
Yeah, but if you have been able to derive the plasma parameters based on these observations, that should tell you something about it.
The problem is that there are several kind of so it's the plasma frequency that I am talking about, that is corresponds to the what is called the middle magnetosphere. And currently there are all, so middle magnetosphere is basically a transition. Unfortunately, I do not have a figure yet. It's basically a region between the closed magnetosphere where the plasma is trapped and the outer magnetosphere where plasma is completely free to flow. And now the currently, although there is a model to give a limit on the plasma in the inner magnetosphere, there is the middle magnetosphere is currently not, we do not have an estimate of the plasma density in the middle magnetosphere yet. So so actually what I am, through the ECME, I am trying to constrain the plasma density in the middle magnetosphere. So it's not, it's in the reverse ways, not.
Okay, all right.
Yeah.
Thank you.
Okay, thank you, Barnali. So